Any questions? Hello, everyone. Good afternoon. Please, I want to know if you can hear me. Can you? Somebody?
Yes.
Okay. Perfect. So, look, I will open the file for the review, but I already post that in Canvas. So you can find that information in Canvas also, okay? With the solutions. Remember that this review is being recorded in Zoom. So you can watch it later if you want to. Perfect. So, first information concerning the exam tonight. The exam contains 26 questions, plus the question from the honor pledge at the end. So please don't forget to shred your scratch paper before you leave the exam and sign for the honor pledge code, which is 2 points. Don't forget that. So 26 questions. Okay, concerning to the review, I brought a series of different questions. At the end of the review, the remaining time of office hours, well, for those not interested can leave. And then after, I will be the remaining time to answer any question or extra question after we finish the review in my office hours on regular time. First question on this review, again, is available from Canvas in your case. Calculate in kilojoules the standard enthalpy change for the hydrogenation of ethine to ethane. The bond enthalpies are given in kilojoules per mole. So the first you need to notice in this case, and also you need to do that on the exam, is that you have an equation for a chemical change, but you don't have the Lewis structure. So it means that in this case, you need to first check if the equation is balanced. And then after you check the equation is balanced, which is the case in this case, you need to draw the corresponding Lewis structure in your scratch paper. Why? Because you don't know if you have a single bond, a double bond, a triple bond, and you won't know what values you need to take. So you need to draw the Lewis structure, in this case, for the C2H2 and for the C2H6. This is something important you need to do before you start to doing the analysis, because the calculation is not that complicated. We use the corresponding bonds, which are broken, or the bonds which are formed, but you need the Lewis structure. So the first is, well, the equation is balanced. 2 carbons, 2 carbons, 2 hydrogens and 6 hydrogens, and you have 6 hydrogens on the right. So the equation is balanced. But then after, we need to see what is the structure of C2H2 and for C2H6, and for hydrogen, which is very simple, is just a single bond in between the 2 hydrogens. So this is what you need to do. I will skip the way on how to determine this basic Lewis structure, but after you apply all what I taught you during the class on how to determine the Lewis structure, in this case, you will see that the Lewis structure for this simple molecule is C2H2 is ethine, is 1 single bond in between the carbon and the hydrogen. This carbon is hybridized sp, and is forming a triple bond with this second carbon, which is also hybridized sp, the single hydrogen on this case. So this is the structure of ethine. And then you have that 1 mole of ethine is reacting with 2 moles of hydrogen to produce ethane. And in the case of ethane, you have only single bonds, as you can see here. Again, you need to construct the Lewis structure based on valence electrons, share electrons, non-share electrons, and so forth. The traditional way on how to determine the Lewis structure. Okay, so now, a second to find the pointer back. With the structure of ethine and the structure of ethane, now we need to proceed with the calculation. So my recommendation is to divide this in between 2 sides, the reactant side and then the product side, because we need the 2 sides to calculate delta H for the reaction. Delta H of the reaction will be equal to the sum of delta H on the reactant side minus the delta H of the product side. So in this case, let's calculate the reactant side. So in the reactant side, we have one carbon triple bond carbon, and here is the energy, 139 kilojoules per mole. And you remember for each ethyl molecule, you have two carbon hydrogens, so it's 2 times 413 kilojoules per mole. But remember that you need ethyne and you need the 2 moles of hydrogen. So for the ethyne, we have 1,665 kilojoules per mole. And for the 2 hydrogens, you have 2 times 432 kilojoules per mole. And when you sum the two, you will have a total for the reactant side, which is 2,529 kilojoules per mole. Okay, now we have that sum of energy for the reactant side, and we need that to determine how many bonds are broken. And then to see on the product side, we need to see how many bonds are formed, okay, and the energy associated with that. So for the ethane, we have in this case one carbon-carbon, single bond, which is 347 kilojoules per mole. And on the case of the carbohydrate single bonds, you have 6. So 6 times 413 kilojoules per mole. When you sum the two, you will have the total of the sum in the product side is 2,825 kilojoules per mole. So now we have the two, and what we need to do is just calculate delta H of the reaction, which is equal to the subtraction from the delta H of the reactant side minus the delta H of the product side, and in this case is equal to negative 296 kilojoules. So it means that the correct answer in this case is answer 4, negative 296 kilojoules. So remember, the key here is check the equation is balanced, then see the structure of the reactant sides, the product sides, and then just do the simple calculation. Okay, now we have a second question in the review, and that question is the following. Which of the following molecules are non-polar? So we have OF2, we have CF4, and we have CH2F2. So we have oxygen difluoride, we have carbon tetrafluoride, and we have difluoromethane. The options are 1, 2, 3, 4, and 5, or all of them. So we need to consider one by one. But before we consider one by one, we need to analyze, in this case, each of the given structures: oxygen difluoride, carbon tetrafluoride, and CH2F2. So we apply the methodology that you, I hope that you learned that till today. For the oxygen difluoride, the first we need to determine is the valence electron. So remember, if you check on the periodic table, oxygen belongs to group 6, and you have one oxygen. 1 times 6 is 6 valence electrons from the oxygen. For the fluorine, we have 2 fluorines times 7, which is the group of fluorine. So 2 times 7 is 14. We assume the 2, and we have the total valence electrons, which is 20. But before, after you have the valence electrons, you need to draw the initial Lewis structure, and that initial Lewis structure locates the most electronegative, the less electronegative atom in the center, in this case, which is oxygen, and the peripheral ones, in this case, the fluorines. Of course, you cannot locate as a central atom hydrogen, because hydrogen is also peripheral most of the time. So, well, it's all the time peripheral. So in this case, we have 2 peripheral fluorines. And remember, in this initial Lewis structure, you need to draw this initial with only single bonds linked to the central atom. Then after, you see, okay, we'll have 2 single bonds, and we remember that per each single bond, you have 2 electrons. So we have 2 and 2, we have 4 chair electrons. So 20 valence electrons minus 4 chair electrons, you will have 16 electrons to distribute. So in this case, remember, both oxygen and fluorine are atoms on the second period, so they will form the octet. And in this case, so you locate that in this case, 2, 4, 6 on the fluorine, 2, 4, 6 in the other fluorine, we have 12. Then we have 2 more on the oxygen and 2 more on the oxygen, we have the 16th. So if you see the fluorine on the left have the octet, has 6 electrons plus the 2 share 8. The center one has 4 and 2 share 8, and the right one exactly the same. So after you have that Lewis structure, you go for, remember, both atoms in this case, the oxygen and the fluorine, belongs to the second period. And then after you do that, you go for the electron arrangement or geometry, and that belongs to the formula AX2E2. A is the central atom oxygen, X2 are the peripheral, in this case 2 fluorines, and E2 because the central atom has 2 lone pairs. For any AX2E2, the electronic arrangement or geometry is tetrahedral. But remember, you need to consider not the electronic arrangement to determine the polarity. You need to determine, of course, the polarity of the bonds is important, but you need to determine the molecular shape. And in this case, the molecular shape corresponding to a formula which is AX2E2 is bent. So in this case, you have the 2 oxygens, the 2 lone pairs on the oxygen, yes, repelling to each other and causing the fluorines to approach to each other. So once you draw the 3D structure, which is bent in this case, you will see that the polarization vectors do not cancel because the fluorine is more electronegative than oxygen. So each one pulls electrons, and so you have a polarization or a net polarization vector towards the fluorines, and that give you a mu or dipole moment which is higher than 0. So this molecule will be polar. So now you see that OF2, okay, cannot be considered because this molecule is polar, and the question is asking you for the non-polar. So OF2 is not because it's polar. Now let's consider the second one. In the second one, we have carbon tetrafluoride. The carbon tetrafluoride, after we apply the calculation from the Lewis structure, we'll see that share electrons 32 minus the 8 share electrons. We have 1, 2, 3, 4 single bonds times 2 is 8. Share electrons will give you 24 electrons to distribute. And we do that on the peripheral because on the central carbon, that carbon has 2, 4, 6, and 8 electrons. So it has the octet complete. So in this case, 6 electrons or 2, 4, 6 for each of the fluorines times 1, 2, 3, 4 is 6 times 4 is 24. So the final Lewis structure will be this one with the carbon on the center and the peripheral fluorines, each one with 3 lone pairs. And that is a formula which is AX4. The central atom has no lone pairs at all. And because of that, the geometry and the electronic arrangement, the two are tetrahedral. So the electronic arrangement is tetrahedral and the shape is also tetrahedral. And because of that, in a tetrahedral, you have a tetrahedron where the center is the carbon. And if you see each one of the fluorines, which is more electronegative because each of the covalent bonds are covalent. In this case, each one of the fluorines are pulling electrons towards it. And all the polarization vectors cancel to each other. And that's why the dipole moment is 0. So this molecule is non-polar. So at least one, okay, we know that this is a correct answer. So carbon tetrafluoride is non-polar. But we need to still see CH2F2. We know that options having OF2 cannot be, but options having CF4 can be, but then after we have that alone or we have a combination, so we need to still see if we have the last one as polar or non-polar. Let's go for the last one, CH2F2. And if you go there, you will see that the initial structure will be this one on the left, yes, based on the chair and the on-chair electrons. And when you have 12 electrons to distribute on that initial structure, you will see that the octet is complete for the central atom, which is carbon. The duet is complete for the hydrogens. Remember, hydrogen can only have 2 electrons. It forms duets. And each of the fluorines is having the octet complete. Fluorine is also on the second period. So you see that molecular electron arrangement is a tetrahedral, and the shape is also tetrahedral. So if you form a tetrahedron back again, you will see that the 2 fluorines are pulling electrons, one to the top, one to the bottom on the left in this representation. And carbon is more electronegative than hydrogen. So carbon is pulling an electron from the hydrogen. So as you can see, you have a polarization vector diagonal top in this drawing, and the dipole moment, or mu, is higher than 0. So that molecule is polar. So OF2 is polar, CH2F2 is polar, and the only one which is non-polar is CF4, and that corresponds to answer 1. So that is the reason why this answer is 1. Now let's do a similar analysis on this second case. This second case is a little bit more complicated because we have elements not belonging to the second period. So in this case, we have different ions. We have iodate, we have ICl2 minus, we have SF4, which is non-ionic, and we have selenium tetrafluoride, and we have carbon dioxide on the 5th. So in this case, the analysis goes more or less the same initially as the one we did before. But we need to be careful in those cases where we have elements not belonging to the second period, because those elements below the second period, 3 period or even below, like the elements we have in here, can expand the octet. So they can have more than 8 electrons around. So you need to consider that. This is the first. The second you need to consider is the formal charges, because you need to see a structure that has the smallest formal charges, okay, or non-formal charges. So formal charge equals 0 as possible. So based on that, we need to construct a Lewis structure. For each, we need to see the molecular shape, and we need to see the electrons which are arranged. Also, we need to check the polarization vectors as we did before, but we need to consider also if the elements involved are or not in the second period or below the second period, and the formal charges. So let's consider the first case. In this case, remember, the question is asking for which of the molecules has a dipole moment. So it means that which of the molecules is polar. So for the first case, we have iodate. So after you construct the Lewis structure for iodate, you will find that the Lewis structure for iodate is this. Yes, on the left. But that structure on the left, yes, after you find that that is a corresponding Lewis structure, because in that case, the structure or the Lewis structure has the lowest formal charges possible on the central atom and the surrounding atoms. So in this case, we have iodate, and in the iodate, we have 1, 2, 3 double bonds, and we have one single bond with a negative charge over the oxygen. When you calculate the formal charge of iodine on the center, you will find that that formal charge is 0. So the formal charge of the remaining oxygens is also 0, and that's why this is the preferred structure. However, you must remember that when you have a system like this, which is conjugated, single, double, you have a chance of resonance. So when you have an atom having lone pairs connected through a single and then a double bond, you have a chance of doing resonance. And if you see the resonance in this case, will give you 1, 2, 3, yes, and 4 possible resonance structures with the formal charge 0 on the iodine, 3 oxygens with formal charge 0, and only 1 oxygen having a formal charge equal -1. So after you construct the hybrid of resonance, you will see that all the oxygens are partially double bonds or partially single bonds, so as you want to consider that. But all of them are not single or not double. And that makes that the bond length in all of them is exactly the same. So this is highly important because it means that every oxygen, okay, every oxygen is able to pull electrons from the iodine in the same magnitude. So the polarization vectors in between the iodine and the oxygens will be exactly the same. Remember, oxygen is more electronegative than iodine. And then if you go to the shape of the electronic arrangement, if you go for the electronic arrangement, you will see that it's tetrahedral. And then the shape in this case is also tetrahedral because the central atom has no lone pairs. So after you draw the tetrahedral structure for this anion, you will find that all the polarization vectors, okay, pull exactly the same. And the reason why all of them pull exactly the same is because all of them are not single, not double, are like something in between the single and the double bond. So the same magnitude, all of them, the same bond length, all of them, the polarization vectors cancel to each other, and that's the reason why this molecule or this ion is nonpolar. So iodate is not the answer. Now let's go for the second case. We have ICl2 minus, and after we calculate the valence electrons and in this case, remember that because we have an anion, you need to add for the sum of the valence electrons 1 because of the negative charge. So you have 22 valence electrons minus 4 electrons share because the initial structure has 2 and 2 electrons share on the bonds. So you have 18 electrons to distribute. You distribute the electrons, but you will see that the chlorine has, each one has 6 electrons each, plus 2 is the octet, and the iodine, which is the central atom, has 2, 4, and 6 electrons in the center. So the molecular formula belongs to this type, AX2, because it has 2 chlorines, A is iodine, E3 because the central atom has 3 lone pairs. So the electronic arrangement for that molecule is, in this case, trigonal bipyramidal. But the shape is linear. When you have a trigonal bipyramidal structure, you give priority for the equatorial positions for the lone pairs. And in this case, the equatorial positions, you will place the lone pairs. So you have 1 lone pair, 2 lone pairs, and 3 lone pairs on the equatorial positions, and in the axial positions, you place the 2 chlorines. And as you can see, the chlorines are axial, so perpendicular to the plane, and the polarization vector from the top cancel perfectly with the polarization vector from the second in the bottom, and that's why this molecule is linear, and the polarization vectors cancel to each other, and that's why the dipole moment is equal to 0. So this one is not also the answer because it has a dipole moment. It doesn't have a dipole moment, sorry, the previous one. Dipole moment is equal to 0. Now let's consider sulfur tetrafluoride. This molecule is really tempting for many people because, as you might remember in my previous example, in my previous question, we analyzed carbon tetrafluoride, CF4. And in the case of the carbon tetrafluoride, the molecule was tetrahedral and the dipole moment was 0. So people confuse a lot carbon tetrafluoride, and they are tempting to just categorize this exactly the same because it has 1 sulfur on the central atom and 4 fluorines around. Like when you do the electron counting, you will see that sulfur has 6 valence electrons, fluorine has 20. For the fluorines, you have 28 electrons, valence electrons. The sum is 34, and you have the initial structure looks very tempting to be categorized like AX4. However, when you subtract the valence electrons, you will see that you need 26 electrons to distribute. And when you do that, you will see that the central atom, which is sulfur, has 1 lone pair. And because that has 1 lone pair, yes, that belongs to form which is AX4E. So the central atom has 4 groups around and 1 lone pair. And that corresponds to CISO. Yes? So in the CISO, you will see that the dipole moment is higher than 0 because the vectors do not cancel each other. So remember that in this case, if you see the 2 fluorines which are on the sides, you locate on the CISO representation here on the left. Yes, you have a lone pair towards the top. Yes, and that creates repulsion. So the fluorines on the sides will go like angle in that case. So the polarization vectors do not cancel, and that's why this molecule is polar. So this molecule is polar. So you find the answer in this case. And well, in the next case, you will find that xenon tetrafluoride is having a molecular shape which is square planar, and the fluorines cancel to each other, and you have 2 lone pairs on the axial positions. So in this case, the dipole moment will be equal 0. And finally, for the carbon dioxide, after you draw the loop structure, you will see that it's CO2 with 2 double bonds. The angles are 180. The molecular shape is linear, and because you have 2 polarization vector, one going to the right and one going to the left in the same magnitude, cancel to each other, and the dipole moment is 0. So as a conclusion from this, we have that correct answer in this case is 3. Sulfur tetrafluoride. So be careful about the shape, the electronic arrangement, and the polarization vectors to determine when it has dipole moment and when it has not dipole moment. Okay, now let's go on the first part of chapter 8, which is also on this. You saw certain part of this on the previous exam, but remember on the previous exam, we just considered the first 3 quantum numbers, and in this case, we can consider the last quantum number, which is the magnetic quantum number, the spin quantum number. So in this case, the question says, which of the quantum numbers, which set of quantum numbers can be used to describe the first electron ionized from the magnesium? So we have different combinations, but you need to remember something important. Okay, what each of the quantum numbers describe. The first quantum number, or the principal quantum number, n, tells you information about the energy. Yes, when it becomes higher, because the energy increases. Yes, and it's telling you information about also the period it has on the periodic table. So for quantum number n is equal to 1, it belongs to the period number 1. Quantum number 2, n is equal to, belongs to period 2, and so far. The second quantum number, okay, which is L, is telling you information about the shape of the orbital. Remember, we have 4 different shapes. We have S, we have P, we have D, and we have F. And remember, the maximum value for L can be n minus 1. The third quantum number, or in this case, ML, is telling you information about the spatial disposition of that. So for the case of the P, for example, we have the PX, PY, and PC. And it's telling you just information about the orientation in the space. The final quantum number is the spin quantum number, which is telling you information if it's rotating just clockwise or counterclockwise, the electron. So the 4 describes completely that electron. Remember that for the same atom, 2 electrons cannot have the same 4 quantum numbers, exactly the same. But in this case, we need to consider the first electrons to be ionized on magnesium. And if you go for the periodic table, you will find that magnesium is Z equal 12, means that it has 2 electrons, and the first electron to be lost is the electron that will give the electron configuration of the similar electron configuration of sodium. Yes, so it is passing from 3s2 to 3s1. So the last electron will be the 3s2 electron. And this is the one, the last electron will be the first to be ionized. The first to be lost to form the first ion of magnesium. So again, magnesium is C equal 12. The electronic distribution for the ground state magnesium is neon brackets 3s2, 1 and 2. And the first that we need to consider is this one. Yes. So the first that we want to deattach and see what are the 4 quantum numbers for that one is that. So for this, you can see that magnesium belongs to group 3. And that's why the first quantum number is 3. Then L is telling you information about the shape. And in this case, remember, is 3s2. And the shape is S, and S corresponds to quantum number equals 0. 1 corresponds to P, 2 corresponds to D, and 3 corresponds to F. Then after, remember that ML goes from minus L to plus L. But because L is equal to 0, the only possible value for ML is 0. So L is equal to 0. And then after, MS can be either plus 1/2 or negative 1/2. Yes, but in this case, not negative is given, so just select those. So the numbers are 3, 0, 0, and 1/2. The most important is that if you see the 2 electrons here, if one is plus 1/2, the other one should be negative 1/2. But it's not the question in this case, but you should know that not 2 electrons on the same orbital will have exactly the same spin. So the answer is, in this case, 2. 3, 0, 0, and plus 1/2. Okay, now let's consider the next. Determine the molecular geometry of oxygen A and all its consecutive carbons, respectively, in the following compounds. So we have this compound. We have HO, CH2, and CHO. Note oxygen A, which is the label, is HO. So in this case, we need to determine the molecular geometry for this first oxygen, for the second carbon, and for the next carbon, from left to right. So we have different choices, but we'll need to do the exercise. So the first is to construct the Lewis structure. So for that molecule, you need to just count the atoms you have, the different type of atoms you have, and you need to determine the valence electrons, then draw the first Lewis structure, share electrons, subtract from the valence the share, and you will have the lone pairs. And then you construct the final Lewis structure. So after you do that, you will find that that Lewis structure is this. Be careful here because I skipped the lone pairs over the oxygen on the left, the OH. This oxygen on the left has 2 lone pairs, as you can see on my right structure. Yes. And the second oxygen has also 2 lone pairs. You can notice also that all the bonds are single except the carbon double bond oxygen you have on the right. Yes. And based on that, you can then after see, okay, let me see the molecular geometry for each of the possible central atoms you have in there. So remember, this is an example of an organic molecule, and you will have an example like this on the exam. Be careful. At least one. I believe it's 2, but at least one you will have on the exam. So be careful about that with multiple central atoms. So in this case, we have multiple central atoms, and the question is asking you about the molecular geometry for each. Questions can ask you about the hybridization. Questions can ask you also about the angles. Question can ask you also about the number of lone pairs. But in this case, or several terms of the same question. So be prepared for that on the exam. So this question is asking only for the hybrid, for the geometry. And because it's only asking for the geometry, okay, well, let's analyze the geometry based on the type of formula for each of the central atoms. So the first on the left is oxygen, and that oxygen, as you can see, has one group on the right, one group on the left, and two lone pairs. So the form of that is AX2E2. And because that is the form, or the general form for that, AX2E2, that corresponds to an electronic arrangement which is tetrahedral, but for that, the molecular shape will be bent. So in this case, we have that the molecular geometry for this oxygen on the left, OH, is bent. Then you go for the second atom to consider the next carbon. That carbon has no lone pairs on the central atom, and it has 1, 2, 3, and 4 groups around. So it means that the general formula is AX4, and for that, the electronic arrangement is tetrahedral, and the shape is also tetrahedral. And here is asking you for the shape. This is other thing that you need to be careful, because the question can be asking you for the electronic arrangement. So be careful if the question is asking you for the electronic arrangement or the electronic geometry, which is the same, or is asking you for the shape. In this case, it's asking you for the shape. So the shape for this first carbon is tetrahedral. Then let's go for the next carbon. In this carbon, we don't have any central atom, and we have 1, 2, and 3 groups around. So the general formula for that is AX3, no lone pairs on the central atom. And for that, you have a molecular geometry which is trigonal planar. Yes, so I show you the analysis, and I, again, will give you reminders. Read carefully if you need to consider electron arrangement or geometry, or you need to consider shape. Secondly, you need to see if the question is asking you about hybridization. And third, you need to pay attention if the question is also asking you about the lone pairs on the atoms. In this case, if I ask you on the left how many lone pairs you have, the answer should be 2. You have 2 lone pairs on the left oxygen and 2 lone pairs on the right oxygen, also if I ask you that. So be careful at that, because you have at least one question related to this. So the answer is the first oxygen is bent, the second carbon is tetrahedral, and the third carbon is trigonal planar. If I go to the hybridization of the first oxygen is sp3, for the first carbon is sp3, and the hybridization for the last carbon on the right is sp2. Okay, now let's go for significant resonance structures. For the acetate ion, in this case, we have acetate, CH3CO2 minus. After we construct the Lewis structure based on the rules, you will find that the Lewis structure is something like this you have on the left. And again, you have an oxygen, okay, which is having a negative charge bonded through a carbon using a single bond, and then you have a double bond. So in that case, you have an electronegative atom bonded with a single bond, and then you have on the next a double bond. There is a high chance of resonance. And in this case, this is the best representation because all of the atoms have the octet complete, and you have the lowest separation of charges and the lowest number of charges. So in this case, in the left part of the molecule, all of the atoms are neutral except this oxygen on the right. So after you see that, you can see that this has 2 possible structures, okay, which are called significant. And they are called significant because all the atoms have the octet complete. Secondly, you have the lowest separation of charges. And even better, you have the highest number of atoms with the formal charge equals 0. So for this carbon is 0, for this oxygen is 0, for the carbon is on the left is 0, all the hydrogen is 0, and the only negative is the oxygen which is also good because the most electronegative atom supports better the formal charge equal negative. So as a resultant, you have two significant structures contributing to the hybrid, and the answer is 2. So that's why the answer is 2. Now let's go for the next question. So this question, as you can see, is also related to the questions we did before. But in this case, the question is asking you about the valence bond theory, which is the last chapter we saw. It's about the type of bonds that you form. Yeah, you have a sigma bond or you have a pi bond. Yes, so in this case, we are not considering molecular orbital theory. We are considering just the hybridization and the bonds that you can form based on the hybridization. Okay, so we have this molecule CH2CH-CHO. That molecule is 2-propanol. And the question is asking you about how many sigma and how many pi bonds you will have. Again, you will have a question like this on the exam. Not exactly the same, but related to. So be careful about sigma and pi bonds in organic structures on the exam. So in this case, the number of sigma and pi bonds in the structure of this is the question. And the first is that you draw the Lewis structure correctly. So after you find the correct Lewis structure, you will see that you have single bonds on the left in between the carbon and the 2 hydrogens. You have one double bond in between the 2 carbons on the left, one single bond with the carbon on the center, and then you have a single bond in between the carbon and the carbon double bond on oxygen and hydrogen. So you have a total of 1 and 2 double bonds. And remember that for each single bond, you have a sigma bond. And for each a double bond, you have 1 sigma and 1 pi. In the case of a triple bond, you have 1 sigma and 2 pi's. So in this case, in this double bond, you have 1 sigma and 1 pi. In this double bond, you have 1 sigma and 1 pi, and the remaining ones are sigma. So now we have the structure. Let's count the sigma bonds. Remember, the sigma comes from the overlapping of orbitals like this way. Yes, longitudinal, and the pi bonds are coming from the overlapping of perpendicular to the plane or parallel in between p orbitals. So if we count the sigma bonds, we have counting from the left to the right, 1, 2. From the double bond, we have the third one, 4, 5, 6, and 7. So we have a total of 7 sigma bonds. And because we have one double bond, here we have 1 pi, we have in another double bond the second pi, so we have a total of 2 pi bonds. So the corresponding answer in this case is 3. Again, you will have a question like this, or combined with the hybridization, or combined with the geometry on the exam. At least one, or perhaps more. So be careful about this type of questions in organic structures having multiple central atoms. So the answer is 3, 7 sigma, and 2 pi's. Okay, let's practice with some other structure. In this case, we need to do the same analysis, but the structure is this: CH3, CH, CH, C, and CH. So after you construct the Lewis structure for this atom molecule, you will find that the Lewis structure for this is this: CH3 with single bonds, then you have a double bond, then you have a single bond, then you have a triple bond. And after you construct a Lewis structure, it's easy to do that because the analysis is simple. Remember, per each double bond, you have 1 sigma and 1 pi. Per each single bond, you have only 1 sigma. And per each triple bond, if you have it, which is the case, you have 1 sigma and 2 pi's. So let's count the sigma bonds. Starting from the left, you have 1, 2, 3, 4, 5, 1 in the double, 6, 7, 8, 1 in the triple, 9, and 1 here, 10. So 10 sigma bonds. And for each double, you have 1 pi. Here we have 1. And for each triple bond, you have 2 more. So 1 and 2 is 3. You have a total of 3 pi bonds. So as a conclusion, the answer for that is 10 sigma and 3 pi's. Okay, now let's go for the molecular orbital theory, the last part of the chapter, which is included for this exam. In molecular orbital treatment of diatomic molecules, what type of molecular orbitals is or are created by mixing an s orbital from one atom with an s orbital from the other atom? So the most important you need to remember in the molecular orbital theory is that when two atoms form a bond, yes, the molecular orbital says, okay, well, now you create a new orbital. So you are not considering hybrid orbitals like in the valence bond theory. You are considering atomic orbitals that when the atom mixes to form a bond, creates a new complete orbital. And that orbital has like a cloud where the electrons are around. Yes, it doesn't consider like this is hybrid, and then you form a new one. No, it's just atomic. When you put them together, it forms a new molecular orbital where the cloud is, and you have a high probability to find the electron in that cloud. So that theory considers that the electrons on that cloud can assume two different levels of energy. One is the bonding, which is lowest in energy and favorable, and one is the anti-bonding, which is up and has a higher state of energy. So we call them the bonding with no start, and the star, which is on the top, which is the anti-bonding. So in this case, if you have, for example, two hydrogens, yes, each of the hydrogens have electrons only on the s atomic orbital. And one electron from one hydrogen and one electron from the other hydrogen will form a bond in between the two, sharing 2 electrons. So the total electrons you need to consider in this case is 2. And because once you put them together, there is a double state, yes, okay, where the electrons can be one lower in energy than the other one. In this case, the overlapping of one s and the 2s and the other one s is just longitudinal. It cannot be perpendicular to the plane. The only ones that can do that type of interaction parallel or perpendicular to the plane are the pi, not the pi, sorry, are the p orbitals that form the pi bonds. But this is not the case. The interaction can be only longitudinal. And because of that, the type of interaction longitudinal becomes the S bond. But remember, 2 states can be assumed. One is highly favorable, is the bonding, and the other one is the sigma bonding, the sigma anti-bonding, which is the sigma star. So the 2 electrons will locate, okay, in the ground state will locate in the most stable one. Lower energy is the sigma 2s. And the sigma star 2s, which is the anti-bonding, is empty. So the 2 possible orbitals are sigma and sigma star. So the answer in this case is 4. So answer is 4, sigma and a sigma star. Okay, now let's consider a molecule which is diatomic. And you can have homonuclear or heteronuclear molecules. If you have the homonuclear, you have N2, you have O2, you have F2, and so far. So remember in class, I explained that you have two different levels of energy, depending if they are with mixing or non-mixing. And some students during my office hours asking me if you need to memorize the increasing way on how to fill the mixing or not or not mixing for the second period elements like boron, carbon, nitrogen, and oxygen, fluorine, and neon. And my answer in that case was not. because the increasing order of filling those orbitals will be given on the exam. So don't worry about that. The most important, because the order will be given like is given on this case, the nitrogen monoxide, but even for those homonuclear molecules will be also given. But you need to remember the rules on how to fill those orbitals from the lowest energy to the highest energy, just applying the same rules that you apply when you learn how to fill up the orbitals for the electron configuration of individual atoms. So the Hund's rule also apply in this case. So for this nitrogen monoxide, which is a heteronuclear molecule, nitrogen and oxygen, you have this following from the left to the right, okay, increasing filling of those orbitals. And the question is telling you, okay, what is the bond order of nitrogen monoxide according to the molecular orbital theory? So remember, nitrogen has 5 electrons because it belongs to group 5, and oxygen has 6 electrons because it belongs to group 6. When you sum the two, you have 11 electrons to distribute. And if you do that distribution, well, in this case, it was even easier. The distribution was already given. So you locate 2 on the 2s, then 2 in the 2s sigma star, then 4 on the pi 2p, then 2 on the sigma 2p, and then 1 on the pi star 2p. If you don't have this number, like 2, 2, 4, 2, and 1, just seeing the increasing order from the left to the right, you will be able, using the Hund's rule, to fill up those 11 electrons. In this case, you have 11 electrons to distribute. But well, here is even easier because the 11 electrons are already distributed here. So once you have that, what you need to do is, okay, so you have, okay, in the bonding, in the first bonding, you have 2. In the second anti-bonding, you have 2. In the bonding on the pi, you have 4. On the sigma 2p, you have 2. And in the pi star 2p, you have only 1. So if you see, if you assume the bonding, we have 2, 4, 6, and 8 electrons on the bonding, and we have 2 and 1, 3 electrons on the anti-bonding. When you subtract the electrons on the bonding minus the electrons on the anti-bonding, you will have 5. And then you just need to divide that over 2 to find the bond order. So the bond order in this case is 2.5. Remember that the bond order is telling you also about the stability of the molecule and how strength is that bond. So in this case, we have a high stability for that molecule, so that molecule exists. If you have a bond order equals 0, means that that molecule is unstable and does not exist. But this is not the case. In this case, well, the question is just asking to calculate the bond order. 2.5 of that molecule exists, and we know that nitrogen monoxide exists. So the answer is 4, 2.5. Now let's consider this. Choose the compound in each set or with the larger magnitude of lattice energy. So look, in this case, we have different combinations: rubidium iodide, sodium chloride, aluminum chloride, magnesium sulfide, copper oxide, and copper oxide, copper 1 oxide, and copper 2 oxide. So in this case, we have different possibilities. And the most important that you need to remember is that in the solid state, for the consideration of the lattice energy, you need to consider a couple of things important. The size of the ions involved is one of them. And also, you need to consider the charge. So you need to consider the charge. So we need to consider those things in order to determine when the lattice energy will be higher. And that will tell you, okay, how strong is that lattice which is forming that ionic compound. That is also telling you, okay, about the melting point. The melting point will increase And you will see that later on solids, that later the melting point increase when you have a stronger lattice energy. You will see that on the next chapters we'll analyze later on this class. So let's consider the first case, rubidium iodide and sodium chloride. So in the case of the rubidium iodide, you have the cation from rubidium plus and the anion from the iodine. So remember, rubidium is located on period 5, and it belongs to the alkali metals. Group 1A is the first group on the periodic table left. And the iodide is coming from iodine, which is located on period 5, and it belongs to group 7A on the stream right. In the case of the sodium chloride, you have sodium cation coming from sodium located on the period 3, group 1A. And in the case of the chloride, you have chloride coming from chlorine, which is located on period 3, group 7A. So in this case, you can see the iodide and the chloride must be analyzed apart. And let's analyze the rubidium and the sodium, which are the cations. So in this case, as you can see, sodium, because it's located on period 3 and belongs to group 1A, it has, following the trends that you learned from the periodic table, it has a smaller size of ions. Yes. So sodium plus have a smaller size of ions and the same type of charges as rubidium. So the size of sodium plus is smaller than the size of rubidium plus. In the case of the iodide, we can see that the size of the iodide is bigger than the size of chlorine because of the location on the periodic table. So in this case, the size of the cation of rubidium and the anion, which is iodide, both sides are bigger in this case than the size of the sodium chloride. And this is important because we need to consider the Coulomb's law. Remember that the Coulomb's law established that the lattice energy is directly proportional to the product of the charges. In this case, the charges are the same, so you cannot make any difference, divided by the distance in between the ions. And because both the chloride and both the iodide and the rubidium cation are huge, so that will have a smallest lattice energy, rubidium iodide smallest lattice energy than the sodium chloride. Now let's analyze the second case. Aluminum chloride versus magnesium sulfide. Look, in this case, I will give you, okay, a very initial analysis, but then after, I will give you certain details that will destroy the analysis that we are doing here for aluminum. And I will tell you the reason for that. So if you consider aluminum chloride and magnesium sulfide, we say, okay, aluminum comes from the cation aluminum plus 3, and the chloride is Cl minus chloride. And on the right, we have magnesium sulfide, where magnesium is plus 2 and the sulfide is negative 2. So in this case, you can see that you have a charge which is plus 2, negative 2, and in this case is plus 3, negative 1. And you will say, well, how will I take the decision? Well, I need to analyze the two things. We need to analyze the charges, and we need to analyze the size. However, if you see aluminum looks smaller than magnesium. Yes. So it's difficult to take a decision. You say, okay. But the thing is that if you consider that in this way, you are doing a wrong consideration. Why? Because aluminum chloride is not ionic. Guys, it's not ionic. Aluminum chloride is not an ionic compound. So the lattice energy for a non-ionic compound, in this case, aluminum chloride is covalent, is by far, okay, less stable. So the lattice energy for a covalent compound is immediately smaller than for any ionic compound. So of the same type, of course. So in this case, magnesium sulfide has two things. The charges are big, yes, and in this case, we cannot consider the aluminum chloride as a aluminum +3 and chloride minus, because aluminum +3 and chloride minus does not exist in the regular aluminum chloride, because aluminum chloride is a covalent compound. So in this case, the magnitude of the charges on the magnesium sulfide will make that, of course, biggest lattice energy, but the reason is not that because the aluminum +3 and the 3 chlorides. No, it's because aluminum chloride is covalent. So be careful about that analysis, okay? So here is a first analysis, but I'm telling you the reason why this simple analysis on the aluminum chloride will not work, because aluminum chloride is a covalent compound, and the covalent compound in this case will have a lower lattice energy than an ionic compound. Now let's do the analysis for the last one, copper 1 oxide versus copper 2 oxide. In the copper 2 oxide and in the copper 1 oxide, we have the same metals, but we have different oxidation states. Of course, the copper +2 is smaller than copper +1, but in this case, the oxide ion is exactly the same. So based on this, okay, copper +2 is smaller than copper +1, and copper oxide, okay, where copper has an oxidation number +2, has a higher magnitude of product. So in this case, you need to consider the size, but when you have a smaller size, but you have a higher charge, that higher charge, remember on the lattice energy consideration for the Coulomb's law, the product of the charges, okay, is directly proportional to the lattice energy. And because the product of the charges is a multiplication, in this case, you will multiply +2 times -2. So that is a multiplication. It will affect by far more the lattice energy than the size in that case. So in this case, the copper oxide will have a highest lattice energy. So as a conclusion, will be sodium chloride, magnesium sulfide, for the reason I told you before, for the aluminum chloride consideration, and the copper 2 oxide. Okay, now let's finally consider some important reminders, in this case applied to the formation of an ionic compound. Which of the following process is endothermic? And to do that analysis, you need to remember one slide during my class. Don't remember exactly if it was chapter 10, but it tells you about the Born-Haber cycle. In the Born-Haber cycle, expressed to you on how a compound, ionic compound, can be formed from the atoms. And that was this figure 9.7. So it's chapter 9, not chapter 10. It's the Born-Haber cycle for lithium fluoride. So if you see in this case, the question is telling you which of the following processes is endothermic. So you need to analyze back a Born-Haber cycle to determine if the process is exo or endothermic, depending if you are going upwards or if you are going backwards or downwards in the case of the Born-Haber cycle. So to understand that answer and to understand better this question, let me go back on my slides and I will show you the Born-Haber cycle. So in this case is the description of the Born-Haber cycle to form an ionic compound. That ionic compound is lithium fluoride from methyl lithium and fluorine gas. So the process will start with lithium solid and fluorine gas. If you consider that, the first you need to remember is the formation of lithium gas from lithium solid. And remember, when you pass from a solid to a gas, that process is called sublimation. And sublimation is an endothermic process. And that's why that process needs is an endothermic process. Yeah, it goes from the bottom to the top. It's not releasing energy, it's absorbing energy. Then you need to break out the fluorine molecule into different fluorines. And that, because you need to break a bond, yes, that requires energy. And that process will be also endothermic. So to break the bond in between the fluorines, also it will require certain energy, and the process will be also endothermic. So from here to here, you need also energy. So the process absorb energy is also endothermic. And then after, you need to deattach one electron from the lithium to the lithium plus in the gas phase. When you do that, when you deattach one electron in the gas phase, that process is called ionization energy. And as you might remember, ionization energy is an endothermic process. So the pass from lithium gas to lithium plus gas, attaching one electron, that is ionization energy, and this is the first ionization energy for lithium. Also an endothermic process. Then after, fluorine gas on the top needs to be transformed into fluoride, because you need to ionize that in order to form the ionic compound. But remember, fluorine is on the group 7A, and it needs only one electron to become neon. And that process is exothermic. So gain one electron, or the electron affinity, is a highly exothermic process for most of the atoms. It's practically zero for the noble gases, because they are highly stable, but for the elements on the right, before the noble gases, is highly exothermic. And because it's exothermic, it releases energy. So now we are going from the top to the bottom, releasing energy. And finally, the process where you combine the two, the lithium plus and the fluoride minus in the gas phase to form the ionic solid lithium fluoride. Okay, that difference of energy, and that is an exothermic process, and that difference of energy is something that we call the lattice energy. Yes, so remember, the lattice energy is the energy which is required from a solid ionic compound to separate the ions in the gas phase. So if you go from the bottom to the top, you will see that on the top we have the two ions in the gas phase. So as a conclusion, look, ionization energy, which is the loss of the electrons, is an endothermic process, and electron affinity is an exothermic process, which is the inverse. And in this case, this is the lattice energy. So doing that analysis, you will see the reason why the answer is 5. So in the first case, cesium plus one electron, the cesium plus one electron, yes, is endothermic or is exothermic. If you go on the analysis here, is similar to passing lithium, yes, to cesium plus to cesium gas. In the second case, yes, so in that case, it's like passing lithium plus to lithium gas. So the reverse process, yes, so the difference in between the two. The correct answer is fluorine gas to fluorine gas, yes, because you are breaking the bonding between the two fluorines, and that process requires energy. If we go here, you will see that in order to break the bond in between the two fluorines and make two fluorine atoms in the gas phase, that process requires energy. So you have the two fluorines attached, and in order to separate the two from a molecule into atoms, that process requires energy. And because it requires energy, it absorbs energy, and that process will be endothermic. So that's the reason why the answer is like that. So remember, the ionization energy is the energy required to complete the removal of 1 mole of electrons from 1 mole of gaseous atoms or ions. The electron affinity is the energy change that occurs when 1 mole of electrons is added to 1 mole of gaseous atoms or ions. And the lattice energy is the energy required to separate 1 mole of an ionic solid into the gas ions. So remember, to do an analysis for that question, you need to analyze the Born-Haber cycle and see what processes are endothermic and what processes are exothermic. So as a conclusion, in this case, energy, the process is endothermic to break the bonding between the two fluorines. And in that case, energy is required from the surroundings. So you have the molecule like tied in this way or linked this way, and the surroundings must submit energy, and that energy will be absorbed in order to break the two fluorines and separate the atoms. So energy is required from the surroundings to break the fluorine-fluorine bond. Well, guys, this is all the review I have for you. And if you have any question, I will go. For those who wants to leave, you feel free to do it. And I will remain in the session till my office hours close at 2:30. That's all, guys. Remember, please read careful each of the questions. I believe the exam is by far easier than the previous exam. My expectation is that you can do really better on this exam. I hope that this review was helpful for you. And I will remain here for any questions you have till 2:30.
I have a question. Yesterday at the Broward review, they were talking about which bond order was stable, and she said that a bond order of 0.5 was stable, and I thought it was anything above 1.
Yeah, look, it depends on if you have a point of comparison. Yes, if you have a point of comparison, you can say, okay, suppose that you have this molecule has a bond order which is 0.5, and this molecule with the same atoms, but perhaps one is ionic and the other is not, and you compare the two, and the bond order for one is 0.5 and the bond order for the other one is 1. You would say, okay, well, the one having the highest bond order, okay, will be more stable, and in that case, the one having a equal 1 bond order will be more stable than the one having 0.5. Yes, but if you don't have point of comparison, it is really complicated to tell perfectly if something is stable or not stable. So you can tell that, well, it's totally unstable when the bond order is 0, and that makes the molecule not to exist. Yes, but if the bond order is higher than 0, yeah, it will give certain stability for the molecule to exist. Perhaps only seconds, but the molecule can be detected. You know what I mean? So that is relative, okay? So if you need to compare in between two different type of diatomic molecules, okay, having the same atoms, but for example, you have one is radical, the other one is cationic, the other one is molecular, and the other one is anionic. So in that case, if you determine the bond order and you see that one is 0.3 or 0.5, the other one is 1, the other one is 1.5, and the other one is 2, the one having the bond order 2 is more stable than the one that has the bond order 1 or the bond order 0.5. But all of them, if they are different from 0, can exist. You know what I mean?
Okay. Yes. Thank you.
So you need a point of comparison. But the most important is that, okay, to exist, you need a bond order higher than 0. If the
Well,
bond
the reason
order
I'm
is 0,
asking,
if the bond order is 0, then the molecule won't exist. Got it?
okay, the reason I was asking is because on a few of the homework assignments, you'd ask for the bond order and then you'd ask if it was stable or unstable.
Yes, that was related to the molecule can exist or not. Yes,
Okay, thank you.
no problem.
Uh,
More questions?
I had a question.
Yes.
Would you be able to go over a question on PLQ 23 now that it's closed?
Okay, let me, who is talking? Because I don't see.
Oh, Michael.
Michael, I want to see you, Michael, please.
Yes, yeah.
Okay, so give me a second, Michael. Michael Mendes?
Russo.
Michael Russo. Because I want to allow you to share, but I'm searching you here. Okay, now I found you. So now you are allowed to share with us.
Okay.
So do it, Michael.
There you go. Could you go over question 5?
Yeah, calculate the average AB bond energy in A6. You have a delta H of formation for AV6, which is that. You have the L delta H of formation for A. You have the delta H of formation for B. And you have the delta H of formation for A2, and you have the delta H of formation for B2. So in that case, well, you need to do several analyses. So remember that the delta H of formation refers to the form of one only molecule. Yes, so you need to write the balance equation for the formation of only one mole of molecules. Yes, of V6. And in that case, you need to write the balance equation, and then you need to fix the coefficients in order to form only one mole of that molecule. Got it? And then once you have that, you need to divide that by 6. So the balanced chemical equation that you write in that case is, well, let's write the equation A plus B. It will produce AB6 gas. Remember to produce one mole of that molecule in the gas phase. Yes. So in this case, the form of A you don't have A alone. You have yes. So you have A. So in that case, if you do that balanced chemical equation, you have 1A plus 6B will form AV6. Got it?
Yeah.
Okay. So in that case, you need to find the energy which is required to form A. So A plus 6B will form AV6. Okay. So in that case, you need to see the energy which is required on the reactant side and the energy which is required on the product side. So in that case, you have the equation already balanced for the forming of 1 mole of AB6. Got it? So what to do? In this case, you have the delta H of formation for AB6, which is that one. And we have the delta H of formation for A, which is that. We have the delta H of formation of B, which is that one. And you have the delta H of formation for A2, and you have the delta H of formation for B2, which is 0 for those cases. So if we calculate that in the simple way, yes, so what do you do? I'm asking you, what do you do in order to see why you think you fail?
So I did like I added up like what A and B would have been. So I did 108.9 plus 170.4, and then
But why A?
because
But
I
why?
just thought that was like why the AB.
No, but you need to calculate the delta. You need to calculate the delta H of formation for AV6. In that case, in order to determine the total energy for the AV6 and then divide that by 6. This is what you need to do.
Yeah, yeah. So I did 6x plus AB equals AB6, and then like I plugged in the values for all that, but then it didn't work.
So let's see what is the delta H of formation for A is 108.9 kilojoules per mole, and 6 times B, which is 170.4. And then you have the delta H of formation for AV6, which is negative 80.2 kilojoules per mole. So 6 times 170.4 plus 108.9 is 1,131.3. $80.2 6 times 170.4, which is B. Where do we have the delta H of formation of B? 170.4. So that times 6 is 1022.4. And 108.9 plus 108.9 is 1033.29 minus 80.2 is 953. Yeah, but that gives us a lowest energy than that. Yes. So, so in that case, we need to find. So look, what we need to is find the delta H of formation for the reaction, which is the delta H of formation for just 1 mole, yes, of AB6 on the gas phase. but we need to find the formation for A, and we need to find the formation for B. And we haven't done that yet, and that's the problem, okay? So what I mean is that we have this equation you have in there. Yes, that is the equation you need to consider. And we need to determine the delta H of formation for AB6 on the right. Got it? Okay,
Yeah,
but
I did that. I tried to do that. Oh, sorry.
yeah, but the thing is that we don't have the delta H of formation of these from the molecule. Got it?
Mhm.
So we need to find that. So we have A2 forming 2A, and that is 0, and 2A will be 2 times 108.9, and we need to do the same for B2, which is 0, that forms 2B, and 2B will be 2 times 170.4. That is going to tell you on the bottom. Yes?
Yes.
And that is going to tell you the delta H of formation for A and the delta H of formation for B. But of course, you need to divide that by 2 because you want to see the formation of only one A and only one B. And that is the value that you need to use. You know what I mean? So you need to do, instead of that, 1/2 of A2 to produce A and 1/2 of B2 to produce B on the right.
Okay.
Okay, so you calculate the formation of A and the formation of B, and these are the values that you need to use on the top.
So then, okay.
So you see my equations on the right?
Yeah. Or could I stop sharing so I could so it could be bigger? Because it's like a small box. I can't see it.
Yes, can you stop sharing?
Okay. All right. Yeah, I can see it now.
Yes, so what you need to is determine, okay, the formation of 1 mole of A and the formation of 1 mole of B using the thermodynamic data. And with those values, these are the values that you will use on the top equation.
Okay.
Got it? And that is the way, okay?
Yeah.
Any case, solve
Thank
it, and in any case, if you have still summed up, just send me an email, okay?
Okay.
So you calculate the formation of A, the formation of B, but remember it's the formation of only one, and then you use those values on the thermodynamic calculation for the first equation on the top. A plus 6B produce AB6, and after you calculate the formation of AB6, you divide that by 6 because you want the average for only one AV bond. Got it?
Yeah.
Okay, nice. Some other question.
I have a question if, oh, sorry.
Oh,
You can go first.
Okay, thank you.
who is asking?
It's me.
Okay, Nidhi.
Okay, can I share my screen?
Yes, give me a second, Nidhi.
Okay.
Now you can.
So I wrote out this question from somewhere, and I just had a general question. If it gives us an equation like this where there's only two main reactions going on, the ionization and the electron affinity, then do we calculate like the change in enthalpy using any other value or only the given values of the ionization energy in this?
Change in enthalpy will only take into account so changing enthalpy will only take into account the ionization energy 1 of sodium and the electron affinity of iodide?
Yeah, is that correct?
Yes, you need to consider the two.
Okay,
Wow.
I just wanted to know if we had to consider the sublimation and vaporization or anything else, if it's necessary to consider those as well.
Yeah, but in this case, you don't need to because both the methyl, in the case of the sodium, the methyl and the cation are in the gas phase.
Okay.
And are in atomic form. So you don't need to break a bond in between the two. And all of them are already in the gas phase. So you don't need to vaporize anything. Yes. And in the case of the iodine monoatomic and the iodide and ion are both in the gas phase. So in that case, you need to consider only the ionization energy 1 from the sodium and the electron affinity, the first electron affinity from iodide.
Okay. If this was like solid and if this was in its diatomic form, then it would be, then I would have to consider the other factors.
Of course, because you need to consider the Born-Havel cycle that I show you in the explanation.
Yeah, okay.
Some other question? I have time. I will give 2 more questions, but we are over time at this moment.
I had a question, more general about like molecular orbital diagrams.
Who is asking?
I'm Catalina.
Catalina, can you show up, please? I want to see the
Hi.
face when I'm talking with.
Can you see me?
Yes. Tell me,
Okay.
Catalina.
Hmm?
Tell me the question.
Okay. Thank you. So I have, it's from the worksheet. Which species is matched with the correct bond order? So I know that you.
Let me give you a chance to share the screen.
Oh, sorry.
Catalina. Now you can, Catalina.
Oh. Sorry. For some reason, it's not letting me share my screen.
Well, can you mention the question anyways?
Yeah. Just is asking about bond order. So which species is matched with the correct bond order? And then it shows the sigma 2s is less than sigma 2s star and so on. So it's a molecular orbital problem. And then it has boron 2 positive, carbon 2, and then so I know that you have to, I know that it involves knowing the anti-bonding and the bonding orbitals. So can you just...
But what is the question, Catalina? Can you say it again?
Yeah, which species is matched with the correct bond order? And then it gives me options. So the first one is boron 2 plus, which is 0, and then carbon 2, which is 1, boron 2 negative, which is 2, carbon 2 negative, which is 3, and then nitrogen 2 positive, which is 2.5.
Okay, in that case, to determine the bond order, you need to know first if you have in front mixing or not mixing. Yes?
Mm-hmm.
Remember, in the exam, I will give you how to fill up, okay, the increase in energy for those mixing or not mixing. But in the worksheet, you don't have that. So you need to go back on my slides and find which ones are mixing and which one are not mixing. So you need to consider if you have boron, carbon, nitrogen, or you have oxygen, fluorine, and neon, because the filling of the orbitals change in energy, okay? And then after, what you need to is just fill up the orbitals depending if they are mixing or not mixing, from the lowest energy to the highest energy, depending on the number of electrons you have for that molecule. For example, if you have carbon 2 plus, means that each carbon from the periodic table has 6 electrons, 6 and 6 when you have C2, not ionic, but because it's C2 plus, it has 1 electron less. So the total electrons that you need to distribute is 11, not 12. And then after you look, okay, well, carbon is mixing or not mixing, and you start to fill up the orbitals based on the Hund's rule. And based on that, you will determine how many electrons you have on the bonding, how many electrons you will have in the non-bonding. And once you have that, then after you subtract the bonding minus the non-bonding divided by 2, and that will be the bond order. And you
Okay.
can fix that problem, okay? So, but in that case, you need to know if the atoms are on the mixing or the non-mixing. Got it? Because if not, you won't know how to fill up the orbitals.
Okay.
But
Okay.
again, in the exam, it will be given exactly the same way as I gave you in the examples. The order of increasing, it will be given to you. What you need to do
Okay.
is just find the Hund's rule, follow the Hund's rule on how to fill up the orbitals, and you won't fail. It's easy. Then you count which ones are in the bonding, which ones are in the non-bonding. So remember, for the cation, for each plus, you subtract 1 electron from the sum, and for each anion, you sum 1 electron to the sum.
Okay. That makes sense. Thank you.
No problem. Sinclair, you have a question?
Yes, I do. I have 2 quick questions for the PLQ. I'm gonna share my screen real quick.
Give me a second, and I will concede you the last question because I'm over time.
It's just regarding 6 and 7. I just want to know
You can
why.
share the screen,
Okay.
Sinclair.
Can y'all see it? Hello?
Yes.
Okay. Oh shoot. Nope. Wrong one. Okay. I
Remember,
just
the
have a question.
PLQ is a practice exam.
Yes, I know. I got a question on numbers 5 and 6. I just want to know, why is this one, I got it wrong for the second time in a row because I couldn't figure out why I figured that this was covalent, but apparently it isn't covalent and nonpolar.
No, yes, it is covalent. That is covalent.
Yes, so I thought the rest of these were ionic. Are they not?
No, they're not. All of them are covalent. All of them.
How? Like,
Well, the difference of electronegativity is not higher than 1.9 between them. So all of them are covalent. So the question is asking you which one of the following is a non-polar. So, okay, with polar covalent bonds.
okay. Higher
So
than-
first, look, the first has a covalent bond, the second covalent, all of them are covalent. But then after, you need to see what bonds are polar. And then after, you need to see the 3D shape to distinguish the geometry of the molecule and determine if the polarization vector cancel or not. For example, in the first case, rapidly, because I can tell you that very easy. In the first case, you have a linear molecule. Yes?
Mhm.
And is only one single bond in between the hydrogen and the fluorine. But fluorine is more electronegative than hydrogen. So that is a polar bond towards the polarization vector is towards the fluorine. So that molecule is polar. In the second case, you have SOCl2. Okay. The name of that molecule is thionyl chloride. In that case, you have a molecule which is, after you do the structure, you will see is AX3, a trigonal planar. That molecule is trigonal planar, and the 2 chlorines are less electronegative than oxygen a bit. So you have a polarization towards the oxygen on the top, and you have 2 chlorines pulling electrons from the sulfur. But the magnitude of pulling of the 2 chlorines and the oxygen will not cancel. So that molecule is also polar.
Mhm.
Yes. And then after you need to see H2 tellurium. And in that case, you need to see if that molecule is not polar or polar. But that molecule is polar because the molecule is bent. Yes. And you have, so the polarization vectors do not cancel. Yes. Tellurium pulls electrons from the hydrogen, and the polarization vector do not cancel. Though the molecule is non-polar, is polar, sorry. And then after you have in beryllium dibromide, that molecule is linear. And because it's linear, then after you have beryllium on the center, and you have one bromine pulling electrons to this side, and one bromine pulling electrons to the other side. So the polarization vectors cancel to each other, and that molecule is nonpolar. So beryllium dibromide, okay, is a molecule that contains polar bonds, but the shape of the molecule makes the molecule nonpolar. Got it?
Okay. And
In the third case, you have a trigonal pyramidal molecule, but in that case, you have a polarization towards the nitrogen. So it's like a pyramid, okay, with a trigonal base. So ammonia, the bottom one, is also polar. So look, Sinclair, to consider if a molecule is polar, you need to see two things. First, if the bonds are polar, and third, and the most important, is the shape, because the shape will tell you if the polarization vectors cancel or not. Got it?
And I just
Wait.
had a question. Oh,
Did you say that the molecular shape is second most important? We first have to pay attention to the actual
The two are
bond?
important. The two are important, but the molecular shape is
Okay.
highly important because you can have polar bonds with no polarity in the molecule. Yes. So the 3D shape will help you to take a decision.
Okay.
So you need to consider the two. The two are important, but the 3D shape will allow you to make a decision. You see?
Okay.
and I was just confused on number 7 as well. So I just didn't understand that either. I think I guessed on that because I got it wrong.
Well, in that case, you need to, which molecule has the most polar covalent bond? In that case, what you need to do is just consider the difference of electronegativity in between the atoms. The one having the biggest difference of electronegativity will give you the more polar bond.
Okay.
And in this case, it should be HCl, I believe.
Okay. Thank you.
No problem. Well, guys, I need to leave a very short question, only my last one. Any?
Yeah, one quick question.
Okay.
Oh, sorry. Why do I know what antibonding orbitals are, but why do they exist exactly? Like,
well, because that is the basics of that theory. So the thing is that so it explains that you can have the two states, because you can have a cloud without nodes and you have a cloud with nodes. Yes. So with a cloud is like this way. In all the cloud, you will have a chance to find the electrons. Yes. So in all the cloud, you will have a high probability to find the electron. That is the bonding. But if the cloud is like this way, so you have like a big cloud here, and it's just together by a point of connection. Yes. So that point of connection is called a node. And when you have a node, that is okay, that makes the interaction highly energetic. And in the point, which is the cloud, you have practically nothing or a very low probability to find the electron. So compare that to a big cloud where you have the probability to find the electron in all of them. So the molecular orbital theory tells that whenever you have a bond, or when you create a new bond, you will create a new molecular orbital, and that molecular orbital will have two states of energy, one with high probability and the other one having at least one node with a low probability to find the electron, but the two exist. Yes,
okay,
in the
thank
ground
you.
state, when the molecule is stable, the electrons have a tendency to have all the electrons in the ground state, which is in this case the molecular orbital bonding. But then after, when the energy increases, you need to fill up the other ones. The other ones also exist. They have a high
Okay.
energy, but they also exist.
All right, thank you.
No problem. Okay, I need to leave, guys. So good luck tonight. Okay, and be careful, read carefully, every question. Again, you have 26 questions plus the honor pledge. And good luck. Read carefully, please, all the questions, and good luck tonight. Best wishes for you.
Thanks.
Bye-bye.
Thank you.
Thank you.
See you then.